Hello everyone. Uh, this is the post-contest discussion of AtCoder Beginner Round 444. I am Hariom Singh and this is TLE Eliminators. Let's get started. Moving to the problem number A. You are given a 3-digit positive integer n. You have to determine whether all the digits are same in n if they are represented in the decimal form, right? So basically you're given an integer n and you have to tell whether it is of the form like 333 or 222 or 456. If all the digits are same, then you have to tell us whether it is true. So you have to tell yes. Otherwise, if the digits are different, even if a single digit is different, let's say if a number is 4 and 9, then 4 and 9 are different. So you have to tell no, right? So this is fairly simple problem. You can just, you know, check it manually that uh, since the numbers are all the numbers are of 3 digits, you can just check whether the first digit is different from the second, then first is different from the third, and then second is different from the third. So if like all of them are same, you have to tell yes, otherwise you have to tell no. So, but I did not notice that it is greater than 100, so I assumed that. So to make the code more modular, suppose that if there were only 2 digits in the number, suppose that n was greater than or equal to 1, and there was some upper bound to it, let's say 999 only, then you can just check whether you can take this number n as a string and just insert all of these characters of n into a set, and then check whether so if you insert it into a set, then there will be just one element because duplicates get removed, right? So I did that only. I just created a set of characters and I inserted all the elements of this string, and I checked whether the size of the set is 1 or not. If it is 1, then all the elements are the same. Otherwise, no. So it passed, right? Moving on to problem number B. Like we can see the test cases of this as well. 444 returns yes. If they're 160, you can just return no. If it is 999, it's return yes, right? Very simple problem. You do it manually or maybe using a set, something like that, right? So moving to problem number B. uh, the digit sum, it goes like the digit sum of a positive integer n is defined as the sum of digits when n is represented in decimal. So suppose you're given some number n and you define digit sum as, suppose you break down all the digits of the number individually. So what I mean by that is, suppose you're given some number 2026, that is in the example as well, right? Let's just choose let's just choose 20195, something like this. So given this number, you can just decompose into individual numbers. So you can for the digit sum of s, digit sum, I'll denote it with ds. This will be 2 plus take this 0 plus 0 plus take this 1, you get 1 plus 9 and this 5, right? So whatever this comes, digit sum, whatever this comes, you're just defining this value as digit sum of some number in decimal form, right? So you have to find the number of positive integers n, sorry, positive integers not exceeding n, whose digit sum is exactly k. So this statement means that you have to find total number of numbers from 1 to n whose digit sum is exactly k, right? So I mean this so the size of n is 10 to the power 5, right? So what does 10 to the power 5 tells you? 10 to the 5 10 to the power 5 tells you that the number of digits in any number will be at most 5. I mean there will be 5 zeros and just a single 1. In 10 to the power 5 there are 5 zeros. I didn't know this. Let me erase it. So this is 10 to the power 5, and all the numbers lesser than that will have uh, the number of digits as 1, 2, 3, 4, 5 only, right? Something like this. So basically, for if I let's just solve a simpler problem. Suppose I give you some number n. Can you tell me what is the digit sum of that number? You can just that we just saw this, right? To do that, you can just extract the digits one by one and add it to a sum counter, and you can just add it to the sum and move on to the next digit, right? So if I give you some integer n, what you will do, you can just iterate it from the back, right? So what I mean by that is, suppose some number is given to you as 3, 4, 9, and let's say 8, right? So what I'm doing is, suppose I have initialized my sum as 0. What I will do, I'll one by one, iterate from the back, and one by one, I will take out all these digits and add it to my sum, right? So suppose I take 8, I add it to my sum, so I'll do plus 8. Then what I'll do, I'll divide this number by 10. Why divided by 10? When you divide it by 10, what it will do, it will shift this number 3498 to what? It will shift it to 349 only, right? This is pretty basic, right? And how do you extract the last digit? You can just take modulo with 10. What does modulo with 10 written? When you divide some number by 10, basically what it does is it erases the last digit. And when you take modulo, it just extracts you the last digit, right? Fairly simple programming trick, right? So what I will do, I'll just take modulo with 10 of the current number. I'll add it to my sum counter. Then I'll shift this number by 1, place to the right. How will I do that? I'll divide it by 10. Right. Again, what I'll do, I will just extract the last digit of this number. I'll extract the last digit of this number, and I'll do plus 9. And what I will do again, I'll shift it by 1. So how will my new number look? It will look like 34. And I'll do it how many times till I get to the point where I'll get only a 0. So if I perform another 2 more operations, what I will do, it will convert to 3, and then what happens again, it will then convert to 0. Why? Because the last digit is 3 only, and when you divide 3 by 10, you get 0. So note that these divisions are floor divisions. So 3 by 10 will return to 0, and you can just stop. So coming to 0 tells you that the number is completely annihilated. It has been deleted completely. So how will I do this? So what we solved now was that how do you find the digit sum of this given number? You can just simulate the entire thing in this problem as well. You can just iterate from 1 to capital N and then check whether the digit sum of this current number n matches k or not, right? So I did that only. And problem B, I just took input n and k, and this checker function, it tells me whether the current sum of digits of the current number is equal to k or not. So how do I do it? I initialize my sum counter, and then while current is greater than 0, that it has not been deleted completely, what I will do, I'll just extract the last digit, which is current modulo 10, and I'll delete and I'll shift it to the right by 1, right? So I do that, and then the loop breaks, and I check whether the sum is equal to k or not. So this thing, sum equal to k, it returns 1 if the sum is equal to k, otherwise it returns 0. So what I'm doing here is that I'm iterating over all the integers from 1 to n, and I'm adding it a 1 if the check is passing me a 1, otherwise I'm adding a 0. So that's fine. I ran this on all the samples and it passed, right? A simple problem. The time complexity will be order of n into the number of digits. So that is fairly order of n into 5 or order of n into 10. Linear time complexity, right? This is fine. This is fine for this problem, right? Okay, moving to problem number C. Okay, this was an interesting problem. You were given sequence of n positive integers A. So basically you are given an array A and you have to find all positive integers L for which the following can occur. So what is the story? AtCoder Incorporation, whatever this is, has released a stick-shaped snap called AtCoder Eco. So a cup contains one or more AtCoder Ecos, each of length n. When Takahashi took the cup, each AtCoder Eco ended up in one of the following states. So basically, you were given a stick called AtCoder Eco, and it had an initial length of L, and you're performing some two kinds of states, right? So what happens? It either remained as one AtCoder of length L. So what are you doing? You just you know if the and let's read further. It broke into two AtCoder whose length sum is equal to L. The length of the AtCoder is the positive integer. After shaking the cup, there were n AtCoder in the cup, and the length of the ith AtCoder was AI. So basically, uh, complex problem statement. So what it actually meant that you are given an initial array A, right? So suppose A0, A1 up to AN, right? Suppose this was your initial array A and you had some initial length L as well. So what you're doing that uh, so what you're doing that you had some array L and you can perform two kinds of operation, right? So that L can be decomposed into two ways. Either you take it the same way that L remains L. Otherwise, you can you know you can break it into two pieces of length x and L minus x, right? That's what the problem says. That it broke into two at equals whose some length sum is L, right? And after checking the cup, the length of it should be AI. Fine. The given input guarantees that there is a set one at least one positive integer L for which this can be occurred, right? So basically, you have to find all possible integers L such that if you perform these operations on some other array which had else, all else. So basically, what I mean by that is, suppose you were given an array which had L, L, and you had L, L, lots of else. Then suppose you perform the operation, let's call this operation number one. I'll use this. Let's call this operation number one. Let's call this operation number two, right? So note that operation number one doesn't do anything to our array, right? While operation number two, it increases the number of sticks in the array by one, right? So suppose this was your initial array A. You did nothing to first number, so this remained the same. So we can just copy it to our new array L. Suppose I perform operation number two on here, to here, right? This is performing operation number two, and I am performing operation number one here, right? So how can I do? So suppose that I break it into of length 2 and L minus 2, right? And suppose here also I'm performing operation 2. So what I can do, I can just take one length as let's say 3 and the other part of the length will be L minus 3, right? Similarly, let's just say that I'm performing operation number 1 here. So if you perform operation number 1, nothing happens to an array and L will just be copied as it is, right? So you will have L. So this is your new final array, right? So this is your new final array which is given to you as the input in the problem. They are calling this as array A. You have to find all possible values of L such that this array can be obtained, right? So if you think about this, you will do not get overwhelmed by this problem. If you make some clever observations, you will be able to decompose it into a fairly simple one, right? So first observation that I made in this problem was that L can, so how large or small can L be, right? Note that in this array, can you tell me one thing? In this array, can any element of this array be greater than L? Is it possible that any element of this array will be greater than L? No. Why? Because if you perform the operation number 1, you just copy this element L as it is, right? While if you perform the operation number 2, what happens? You're just decreasing it. Suppose the length of you just decreasing the length of this given uh, you know AtCoder repo into two parts, right? So definitely each of these individual lengths will be lesser than L, right? This will be lesser than L and this will be lesser than L, right? And the sum will be exactly equal to L, right? So our first observation is that no element of this array will be greater than L, right? Okay. What about the max element? If you look at this, you can just say that either L can be equal to the max element or L will be greater than the max element, right? So there are two more things. Maybe I can write here that either L is equal to the max element or L is greater than the max element, right? This is our first observation. The second observation is that you are performing this operation only once. So if you see that in the first case, I can just take that if I fix that L is the max element of the array, then I can just remove all the max elements, all the occurrences of the max element from this array. I can just focus on what I can just focus on all the elements which are lesser than L, the max element, right? So if I focus on the smaller elements, suppose just take this example. I'll take this example. Okay, so maybe I cannot copy it like this. Yeah, right. Suppose I take this, then suppose if I fix that my max element is 10, right? The max element of this array is 10. Then what I'm saying that my L will be either equal to 10, or it will be some value which is greater than 10, right? So suppose that I say in the first case I say that my max element is 10. So what I can do, I can just delete all the occurrences of 10 here. So right, I deleted 10. Then what I'm left with is 5 and 5. So what I will do, I'll just check for each 5. Can I pair it with some other number which is complement to it? What I mean by complement, suppose that if I say this element is x, can you tell me what will be the complement length of it such that when you merge this x with some other element y, then your total length will become L? So what I'm saying that suppose this element is x, what should I match it with? That is x plus y. What should I match it with such that the total length becomes y? Total length becomes L. So basically, we are trying to find y with a fixed x and fixed L. So what is y? This is L minus x, right? And this is where the problem decomposes. So what we have to do, we just have to check whether each 5 can be paired with some other number such that the total sum becomes 10, right? So what we are doing, we are going to find y such that what is the total length L that we fixed? That is 10. And what is the length that we fixed? That is 5. So we are just finding whether 5 exists in this array or not. So for to this 5, we have to complement another 5, right? So is this 5 be able to find this 5? Yes. So 10 is a valid length, right? So this is the first case. Let's just take a look at the second case where L is greater than 10, right? So in the case where L is greater than 10, what happens is that all the elements of this array have to be paired with some other element of the array such that all of them are able to complement each other. What I mean by complement? Exactly this. That for all the pairs that exist in the array, their sum should be exactly equal to L, right? So if I fix that my length is greater than 10, right? then what I can do, I have to just find pairs of numbers. Suppose this is the array that I'm talking about. Then what I have to do, I have to find some pair of numbers. Suppose this is getting matched with this, right? And let's just say this element is getting matched with this. And let's just say this one will be matched with this, right? So what I'm saying is that each element of this array has to be matched with some other element of the array such that all the corresponding matches, they sum up to exactly L, right? This sum has to be L, this sum has to be L, and this sum has to be L as well, right? So now this problem decomposes into a simpler problem that we have to check and find whether there exists some set of possible values of L such that when we are, such that we are able to pair all the elements of the array with each other such that the sum of each pair is exactly L, right? Pretty long statement. Let me write it. You have to find the set of values of L such that you are able to pair all the elements of the array with each other such that sum of each pair is L, right? This is what we have to find, right? And if you notice carefully, okay, let me just make one more observation and then you will be able to, solve this problem on your own, right? Suppose the given array looks like this, right? Suppose the given array looks like this, and you have some elements here, one, two, three, four. Let's just take four elements for now. Okay, let's just take this subset of the array that we are talking about, these elements only. Then, is it ever optimal for me to pair this element with this element and uh, this element with this element? This is never going to be possible for me. So if I want the sum of these to be same, right? Why? Because let's just call uh, this as A, this as B, this as C, and this as D, right? So what I'm saying, let's just call this as pair number one and this as pair number two. All right. So what is the sum of pair one? It is nothing but A plus C. And what is the pair? What is the sum of pair number two? We choose different color. This is nothing but B plus D, right? And what is the main constraint that we have put in this problem? We want the sum of both of these pair to be exactly equal to L, right? Since both of them are equal to L, they are also equal to each other. But is it possible for them to be equal to each other? No. Why? Because if you compare A plus C and B plus D, then you can notice that B is greater than A, right? Why? Because B lies in the number line after A, so B is greater than A and D is greater than C, right? So I'm saying that B is greater than A and D is greater than C, right? And if you add these numbers, if you add both of these inequalities, you will get A plus D greater than, uh, sorry, you will get A B plus D will be greater than A plus C, right? And you want B plus D to be exactly equal to L and A plus C to be exactly equal to L. So they have to be equal. right? They do not should they should not be, greater than or equal to. They should not be greater than each other, right? They have to be exactly equal to each other, right? So it is never optimal for us to pair such that we are getting an intersection point here, right? So what is the only possible way you can pair such that there is no intersection among them, right? So how can you not form any intersection? There are only two ways by which you cannot, find any intersections. One way uh, is that you choose some, uh, you know, you know, you just choose an array and some element in here. These are the elements 4, 5, and 6. You pair this with this, you pair this with this, you pair this with this. But this is clearly not working because some of these will be definitely lesser than the sum of these, right? Because they are in the sorted form, their sum will be lesser than the sum of these, so, and they cannot be equal to each other, right? And the only possible way that you are left with that you might be able to guess, such that there is no intersection and the sum can be equal to each other, is only this, where suppose one element is here, another one is here, third is here, fourth is here, fifth is here, sixth is here, and you're pairing them in this manner. One gets, sorry, this element one gets paired with the last element, this element gets paired with this element, and this element gets paired with this element, right? So in this case, we are not having any kind of, intersections, and intuitively you can also see that if you pair the minimum element with the max element, it is possible that when you move this pointer to here, this element sum will get this sum gets will increased by this difference, and it will get decreased by this difference. So you get plus here and minus here, and the sum can get conserved, right? So the only optimal way you can pair the elements is in this manner, right? So you just pair the first element with the last element, second with the second last, third with the third last, and so on and so forth, right? And that's what I did as well. I so summarizing this problem, you were you know given some set of L's, and you can perform two types of operations. Either you copy the same element L as it is in the array, or you can just decompose it into two set of numbers such that its sum is exactly equal to L. Suppose there was L, you can just take 2 and L minus 2, 3 or L minus 3, right? And we made two observations. First observation was that no element of the array, the given array, can be greater than L, right? So either the fixed element L can be either equal to the max element, or it can be even greater than the max element, right? So we saw this example where if you fix the L as the max element of the array, then what you can do, you can just remove all the occurrences of the max element and check whether all the complement sums are equal to the max element or not. So that can be done using a map or a set or a multi-set in whatever way you are comfortable with. Then we saw that what is the optimal way of pairing the elements such that you are able to pair all the elements, right? And we decomposed the problem into this standard problem where you had to, uh, pair all the elements of the array with each other such that the sum of pairs is exactly equal to one another and they're equal to L, right? Then we saw the only three ways you can pair the elements, two of which got disregarded because they are rejected because they are not, optimal. We saw that if you find any intersection, then the sum of one pair will be definitely lesser than or greater than the other sum, and we want them to be equal, which is not possible. We saw the second case where the intersection is not possible, but the sum will definitely be, in the increasing manner, and we want them to be same. The only way you're left with is that you pair the one element with the last, second with the second last, third with the third last, and so on and so forth. Right. So the code is pretty simple as well. Okay. Let me see. Right. This is the code. Right. I just took the input. I sorted these arrays. So why I'm sorting this? Because I want to pair them in this manner so that the smallest element gets paired with the largest manner, right? So what I did is that I'm considering the first case where, you know, where was the first case? The first case where we are fixing that, our L will be equal to the max element. This is our first case. And our second case will be L greater than or equal to the greater than the max element, right? For the first case, you can just remove all the occurrences of the max element. So what I did was that I chose the right pointer and I'm decreasing R as long as it is equal to the the max element, because if this is sorted, the last element will be present at the back of the array. So as long as it is the R pointer is equal to the last element, the max element, I'm just decreasing it, right? And you can just check whether if all the elements of the array are same, then you can pair all the elements, right? You can just suppose that all the elements of the array were same, which means that all the elements were L L L. You could have copied this entire array as it is without performing the operation number two. So your final array will also look like L L L only, right? So this final array is also going to look like L L L, right? So I just inserted, okay, fine. This is, I have created a set, and note that your answer will not be, greater than or greater than two or three, because either you know, choose the last element of the array, or you choose some other element of the, such that you are able to pair all the elements, right? So what I'm doing is that if not all the elements of the array are deleted, which means that R is greater than or equal to zero, and to and this is a fairly simple thing, that if you want to pair elements with each other, the number of elements should be even, right? So I did that as well. So in zero based indexing, you have to check whether the current element that you're standing at has to be at an odd index, right? So I did that. If these two conditions are true, I just did two pointers. The left pointer is at zero, the right pointer is at the right, and I'm checking whether the total sum should be equal to the max element or not. Right? If it is equal to the max element, I'm just maintaining a flag. So it will tell me whether I have successfully paired all the elements with each other or not. I increment them and then just check whether the all the elements are paired or not. If they're paired, I'm just inserting the last element of the array into my answer. Then the second case comes where we just have to, choose some element greater than the last element of the array as your uh, result. So the pair that you're trying to optimize for is the first, this array is sorted, right? So what you're going to do in this case only, you want to say whether the sum of first and the last should be equal to second last and the second, and something like that, right? So all of these pairs, you just check whether the sum of all of these pairs are same or not, right? So I did that only. I just created a sum. I'm just checking whether the sum of the first and the last are equal or not. If they're all equal, I'm just inserting it in the answer and then just printing the answer, right? Now, what is the statement? The statement is basically, n is odd or not. So you might have seen this. What does n and 1 tell you? N and 1 tells you whether n is odd or not. When you XOR it with 1, you just get it the reverse. N is even or not, right? So to pair all the elements, you need all the elements to be the size of the array to be even, right? So I did this, and it is working fine, right? Fairly simple problem. No, not simple. Interesting problem, right? Moving on to problem number D. Okay, this one was simple. You were given uh, an array A, and so you know, suppose you're given an array A, and then you denote B, array B, such that BI is denoting the concatenation of AI number of ones, right? So basically, suppose you were given, let's say A equals to, let's say 3 and 5, right? Then you can denote B as what? Your array B will be 3 ones and 5 ones. So it will be 1, 1, 1 and 5, 1, 1, 1. 1, 1, right? This is going to your array B, right? And what do you have to tell? You have to find the sum of all the elements of the array B. So basically, you have to find the sum of this array B. Can you do it naively? No. Why? Because A is 10 to the power 2 into 10 to the power 5. So in the worst case, you will have all the elements as 2 into 10 to the power 5, and then 2, and then all the elements, all of these, elements are going to be very large, right? And you cannot possibly store it in some integer or long or whatever you are going to use, right? So, but if you notice carefully, you will notice the pattern that all the elements are going to be 1. So can we take advantage of it? Definitely, right? Suppose to solve this problem, it's just implementation problem. You just need to know how do you actually add the numbers, right? Suppose that I'm telling you to add 33 and 44. No, not 33 and 44. Let's just say 469, right? Let's not 469. Let's just do 461, right? How do you go about adding these two elements, right? How do you do in elementary classes? You just take 3 and 1. What is the sum of 3 and 1? You just take 4, right? You just take 4. Okay, let me choose this number as 5. So this number is 5, right? What happens then? 5 plus 6, this is 11. So do you write 11 here? No. Why do we not write 11 here? We are just going to take the last element, last digit as the base, and we are going to transfer this other thing as a carry. So what will we do? We'll just add 1 here. And what will you do? 4 plus 1 will be 5, right? So your final result is going to look like, the final result will be 514. So what we did just right now? We just take the sum from the previous. We take whether we check whether there is a carry or not. If it is, we just add it to a corresponding sum, and we propagate, we just, recursively just do this thing. What I mean by that is, suppose you were given 469 and you had to add it with itself, right? So what you had to do, you just, add these corresponding digits and check whether you get a double digit number or not. So if you get a double digit number, you're just going to take the rightmost digit of that number as the base, and you're going to propagate everything as the carry to the next addition, right? So you're just taking 18. So what you'll do, you'll just take 8 here and 1 here. Then you're not just going to consider 6 plus 6, you're also going to consider this one as well. So you'll get 6 plus 6 plus 1, that is 13. So I'll get 3 here and 1 here, and then 4 plus 4 plus 1, which is 9, right? This is how you do addition. So in this problem as well, we are going to do the same thing, but in a different manner, right? So in this problem, you just see that all the elements are going to be ones, right? So instead of looking at just directly adding these numbers, we can rather look at how each number is going to influence the positions of the final result, right? What I mean by that is, suppose you are given three additions, 1, 1, 1, 1, 1, and let's just say 1, 1, 1, 1, 1, right? If you look carefully, this one is going to influence only the last digit, right? So what you will do, all these positions which are present at position number 1, they are going to influence the last digit, right? So you get 3. And how do you get 3? You get 3 from each of these contributions, right? This contribution, this contribution, and this contribution, right? Similarly, in this case, you're getting uh, 3 from all of these digits from the similar contributions. But if you look at this position, if you look at carefully at this position, only first and the last number are going to contribute, and this number is not going to contribute, right? What does it tell you? It tells you that if you have some number, let's say x number of ones, x number of ones, x number of ones. Hashtag means the number of, or maybe count of, right? If you have x number of ones, then how many positions is it going to influence? It is going to influence all the positions from 1 to x, right? As we saw here, the number of ones in this number is 2. So it influences how many positions? Only 2 positions, right? So this sum was 3. And with how did we get 3? We got 3 from here. Why is it not working? We got 3 from here, here, and here. So this contribution got from here. But there is no contribution of this number here, right? This is not valid, right? So we saw that if any element of the array A is x, then it is going to add 1 to all the elements, to all the positions from 1 to x, right? So how do you go about solving this? There is so how we are going to do this? We are just going to maintain some new array A. Let's just call it position or maybe count, where we will add all the contributions of each of these numbers from, suppose if you get some number x, then what you're going to do, uh, suppose this is position, let me use this, let's just say this is position number 1, this is number 2, and this is position x. Then you're going to do plus 1 in this entire range, right? By plus 1 I mean that you're just going to add 1 to all of these positions from 1 to x, right? How do you do it smartly? You can use different series. What is different what is different what you can do, you can just add plus 1 here and a minus 1 at position x plus 1, right? And in the end, after propagating all of these values x's, you're just going to take prefix sums, right? So what will happen, you just standard difference array trick, you'll get 2 from here, and when you propagate all of these, when you get here, this plus 1 will negate this minus 1, and the change made by plus this x will be negated, right? So this is standard difference array, and then that is that as that only. So basically we can take the difference array, and then you can just do simulate this entire adding process. So this was the entire problem. This was fairly simpler than the problem number C. What you had to do, you just had to interpret these numbers as plus ones, and then you had to you know at each position you have to look at each position, how that position is going to influenced by some other number. So we saw that if some number x is there, then it is going to influence all the positions from 1 to x, right? How do we do plus 1? We can just do a difference array, and then after doing that, we can just perform this carry operation, the simplest addition that we learned in elementary classes. We're just going to simulate that only, right? Let's look at some sample test cases. This one is too large. All of these are too large. Okay, this one is fairly simple, right? But this one is easy. There's no carry involved, right? So in this, all of these numbers were triple ones. So these numbers were triple ones. So how? So maybe we can look at it, right? So you had one, 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 and let's just say this is our position array, right? So this one is going to add. So sorry, all of these ones are going to add plus one in all the positions from 1 to 3, right? So these are the positions. So this number is going to add uh, so this number was 3, so this is going to add plus 1 in the range from 1 to 3, right? And how many numbers of the form 3 are there? There are 4 numbers. So you're just going to multiply this by 4, and the final result that you get is 4, 4, 4, right? And this is going to be your final answer, right? There's nothing much about it. We can just take a look at the code, right? So what I did was that I took the input, and then I just found the max element of this array. So basically, we are going to do the difference array thing. So for that, you need to know what is the max element of this array, so that you know uh, the max position that you can access. Right? I did that, and then I did the difference array thing that you add one to this position, and for some integer x, you just subtract minus one from the position next to it. So I do x plus one at the position x plus one. I do minus one. Then I do the propagation thing, the prefix thing, that I take all the contributions. So after this, my entire count array will have the contribution of all the numbers, right? But you'll notice that at some positions you will have some numbers greater than 10, right? And in decimal form, you cannot have any element greater than 10. So to fix that, we are going to perform the carry thing. So what I'm doing is that how do you go about taking the carries? So basically, you just take the sum which is present at this position and the carry that you previously got, and you take the the modulo 10, the thing that I have explained in problem number B. So you just take the last digit of the last digit of the number, you save it there, and you propagate everything back to the next number, right? So I did that only. So the current number will be the previous carry that I got, and the pull and the contribution that I have here, modulo 10. So I just take the last digit of that number, I push back into my answer, right? Then what do I do? I just take just I add this number to the carry, and I decrease. Since I removed the last digit, I just shifted it by one. So I just divided it by 10, right? So I did that, and I pushed back the last carry. And note that it might be possible that we are just pushing back lots of leading zeros into our answer. So I just checked whether uh, I have zeros in my answer or not. So if I have zeros, I just remove them. And note that since we are pushing back, our answer is going to be in the reverse form, right? Since we are iterating from back, so I just reversed my entire array and I printed that, right? So basically, you had to think about how each position was influencing the final position array, and then this was fairly simple. This was pretty standard, right? You might have done it some in other problem, right? Okay, so the last problem of our discussion, this was a very interesting problem. So you were given an array. Okay, for the time complexity of this code, this is linear only. Why? Because I just am accessing the maximum limit of the array, which is 200 per 5 only. I think, yeah, 200 per 5, and I am not doing anything complicated here. I'm just performing the carry operations. These are order of n, and the space is also order of n, right? Moving on to the problem number E. This is good problem, right? You are given an integer sequence of length n and a positive integer d. So basically, you're given an array A and a number D. You have to find the number of pairs L to R such that both of these conditions are true. So basically, you have to find the interval L to R such that any two elements of the interval L to R have a difference of at least D. So what they mean by that is, uh, suppose that uh, you have some array A, right? If you have some array A, no, you have some array, oh, you have some array A, and you're taking only you're only considering this subarray of L to R. Then they are saying that all the if you take any element from this, any two elements from this subarray, right? If you take any two elements of this subarray, let's just choose this element as and this element, then let's just call them X and Y. Then they are telling us that the absolute difference of all of these pairs is going to be greater than T, right? So this difference is going to be greater than D, greater than or equal to D, right? And what we have to do, we have to find all such pairs of integers L to R such that this condition is true. So let's look at constraints. It is n into n is 45, A is pretty large, D is pretty large, right? So if you think about the brute force, so basically you can just iterate over all the pairs of L and R, and in each pair you're just going to check whether this subarray is good. And to check whether each subarray is good, you have to another form, like suppose that if I give you some integer L to R, right? If I give you some subarray L to R, how are you going to check it? The first thing that can come to your mind, that you're going to say that I'm just going to iterate over all the pairs of x and y, and I'm going to check whether the subarray difference is greater than or equal to D for all the pairs or not. If it is failing for any pair, then you know uh, the subarray L to R is not good, right? But if you think about this x to y, right? Suppose I say that this interval L to R is sorted, right? Sorted by what do I mean by that? By sorted, I mean that all of these integers are arranged in increasing fashion, or maybe let's just call it non-decreasing fashion, right? So let's just say the number here is A, B, C, D, and E. And note that my claim that I'm making here is that I'm saying that all of these adjacent differences, um, all of the adjacent differences are greater than or equal to D, right? This is my claim. Suppose that if this condition is true, then can I say that this subarray is good? Obviously. Why? Because I say that this subarray is sorted. So definitely C is greater than B is greater than A, and similar pattern will follow for D and E as well, right? And what am I saying? I'm saying that C minus B is greater than or equal to D, and B minus A is going to be greater than or equal to D as well, right? Now my claim is that C minus A will also be greater than or equal to D. This is my claim. And this is fairly intuitive as well and mathematical as well, right? Suppose that you are given some numbers, let's say 1, 3, and 5, right? And I'm saying that difference between 3 and 1 is greater than 2, greater than or equal to 2. Difference between 5 and 3 is also greater than or equal to 2. Then definitely the difference between 1 and 5 will definitely be greater than 2, right? This is fairly intuitive. And you can also obtain it mathematically. You can just add these two equations, right? When you add these two equations, you'll get C minus B plus B minus A. So minus B and plus B will get cancelled, and you get C minus A is greater than or equal to 2D, and definitely 2D is greater than D. So this condition is following, right? Okay, right. So my claim is that if the adjacent differences are greater than or equal to D, then uh, this subarray is definitely good, right? Now, suppose that somehow by some magic, I have maintained a good window. What do I mean by good window? A good window is a sub-array such that all the elements, such that all the adjacent element difference is greater than or equal to D, right? And let's just say in this sub-array you are having four elements and they are in sorted order, right? So and note that I'm adding some element x to this array, and I need to check whether if I add this element x to this good window, is my window going to expand? Is my window going to accept this element, or is it going to reject this element? Right? What do I mean by that? Is that I have to check whether if I incorporate this x as well into this window, then it does not form any conflict with any other element of this array. Right? What do I mean by that? I mean by that is, suppose that this is some, let's just call this element is x, and let's just say that any arbitrary element of this array is y, right? So what I'm saying is that the difference between x minus y, its absolute difference, this absolute difference has to be greater than or equal to d. But contrary to it, I'm saying that a conflict occurs. I'm saying that a conflict occurs if this condition becomes false, right? What I mean by that is the absolute difference, that is x minus y, has to be lesser than d, right? If this condition becomes true, then a conflict has occurred, and I'm not able to add this element x to the array, x to the current good window, right? And if I have to add this element x into this window, I have to delete all the occurrences of number y for which this condition is true, right? I have to delete all the elements from this window y such that this condition becomes false, right? So that this condition becomes true. So how can I write this condition as? I can write this as uh, x minus y is lesser than d, or it is greater than minus d, right? Fairly simple. Then I can write y as greater than or equal to x minus d, and it is greater and it is less than x plus d, right? Basically, I just subtracted x from both the sides. So you get d minus x here and d minus x there. And I then multiply both of these sides by minus 1. So you just get x minus d and x plus d. And you invert the inequalities, right? Right. So this condition. What do I mean by this? That if you choose any arbitrary number from the window, then if this condition is becoming true, then you have to remove this element y from the array, from the good window, right? So this was the breakthrough for solving this problem. So what I did for that is I'm trying to maintain this good window, and if and suppose that if I'm going to adding some other element to this good window, I'm going to remove all the occurrences of y such that this condition is true. And since after removing all of these numbers, I'm just going to add the current element to the good window, and I'm going to check the where was my last L pointer, such that this what was the starting point of this good window, and then we can just say that if let's just say this was L here, and you added some element R, then if this pair is good, then all the pairs are good for this L. What I mean by that is if you're able to pair this with this subarray is good, then definitely all these subarrays as well are good, because the adjacent differences are going to remain the same, right? So if some L is good, I'm going to add the length of the subarray to our answer. So our answer will increase by this, right? So now we have some ideas for solving this problem, but there are some challenges. That note that uh, to check whether to maintain a good window, I can do that maybe using 2 pointers or something. But to check uh, whether some whether some element exists in this array such that this condition is becoming true. To check whether this condition is true, you have to iterate over the entire length of the window, right? And that is going to be order of n square, right? For adding each element of this array, into the window, you are going to iterate over the entire length of the window, and then you're going to add it to it. So basically, that is going to TL, right? You have to do it better, right? So for that, I used maybe uh, some data structure known as Fenwick tree or Selmic tree. So basically, what I'm doing is that these numbers from 1 to 199, I have compressed the coordinates of these numbers. So basically, what I mean by that is, suppose that you have some number, uh, let's just say uh, 10, some number 15, then other number 15 as well, then some number 20. So I've compressed the coordinates of this entire array. So coordinate compression is another trick in computer programming. You should look into that. You can look here. Mm, Here, custom comparison and coordinate compression. How do you go about? You just can read this, and this is pretty, useful in this in computer programming, right? So basically, what I did was that I can just take this one and I can link it with uh, one, and I can link this with two, this with two, and this with three. So basically, if I'm going to compare the numbers 10 and 15, comparing 10 and 15 is exactly same as comparing 1 and 2. Comparing 15 and 20 is exactly same as comparing 2 and 3, right? So that's what I did. So for this problem, what I did was that what I'm going to do is that I'm going to let's okay. First of all, this to check whether some element exists in this range x minus d to x plus d. What I can do, I can literally form this range, right? So for my entire window, I'm going to check whether some element is present from x minus d to x plus d, right? So if some element is present in this window x minus d to x plus d, right, then I'm going to denote 1 if some element is present there, and I'm going to denote 0 if some element is not present there, right? And what I have to do, I have to check whether if the sum of this range, if the sum of this range is going to be greater than 0, what does it mean? That at least some position exists in this interval such that the sum is greater than 0, which means that at least one position exists in this interval such that any value in this interval is set, right? Which means that exactly mm, uh, at least one value y is present in this interval, which is going to conflict with our current x, right? So what do you have to do? You have to remove that occurrence of y from this interval, right? So how do I form these intervals, and how do I check whether the sum of the intervals, whether some subarray is greater than 0 or not? So to do that, I use Fenwick trees. So basically, they are data structures which returns you the sum, uh, some range sum, or you can just also update. So basically, this is difficult to uh, explain without code. So maybe let's just uh, use our code. So basically, what I did was that, suppose in this summary, what I did. So a basic idea is that I'm going to maintain a good window in which all the elements originally are not conflicting with each other. And when I'm going to expand this window, I'm going to check whether I'm going to compress the coordinates such that we are not, if you do not do it, then the size of your pen victory will be from 1 to 199, which is definitely going to MLE, memory limit exceeded. So to expand our window, what I'm going to do, I'm going to check whether I'm going to solve this equation x minus y, the absolute sum of that should be lesser than d, and I'm going to say whether there exists some y such that it is from the interval from x minus d to x plus d. If some y exists in the interval, then I'm going to remove all such occurrences of y such that the sum from this interval is becoming 0, and then I'm going to x to my answer, right? When I remove y, I'll also update my left pointer of our subarray, right? It will get incremented, right? And then my L1, then my window size will shrink, right? And after adding my entire L to R, now this window will get updated, and this will be a new window, right? So how do we do that? To check whether the sum of some subarray is greater than zero or not, I'm using fin trees for faster, access time. And let's just see the code how I did that, right? And I also told you that if some subarray from L to R is good, then you can just choose any of these lefts from L to L, from any of these lefts from L to R. So the total number of possible L's for a given R is just the size of this array. So this is R minus L plus 1, right? So how did I do it? So basically, I just took the input and then took this is just coordinate compression. So basically, in that coordinate compression, we just make a copy of this given array A. We sort them and we remove the we remove the duplicates from this array, such that suppose that if you had 10, 15, 15, 20 as your array, then you will get 10, 15, and 20, right? And then what you're going to do, you're just going to return the position of each element in the sorted order, right? So I did that only. I just returned the lower bound plus one, so to make it, so that we not run into zero issues, right? You can also remove, plus one from here, but then your implementation will change a bit, right? Then what I did, I just created the size, then created the Fenwick tree. So my Fenwick tree is pretty generic. I'm just using, some function from L to R. So this query will return me the uh, sum from the interval L to R, right? And I have also the functionality of adding some element to some position, right? So how do I do it? I just create a segment tree, and this L pointer denotes the leftmost point of the R current window. The R pointer is going to denote the element that I am going to currently add to my good window, right? So what are low and high? So basically, you saw that uh, by solving this equation, we get our low value, that is the left point R interval that we are going to use, is x minus t, and this is x plus t. So how do we do it? So you're just going to, this is true, so that this means that y is going to be greater than or equal to, let me use another sketch, right? So here y will be greater, so this, to convert it to greater than equal to, it will be x minus t plus 1, x minus t plus 1, and this is going to be lesser than x plus t minus 1, right? And note that in order to check whether some subarray after adding x is good or not, all I need to do is to check just the element which is strictly just lesser than it and strictly just larger than it, right? Because only adjacent elements matter, right? As we proved here only, that if you have some elements from A to E, so if you have some five elements and you have to check whether some element is good with the current subarray or not, you can just take the minimal sum and check whether this minimal sum is greater than D or not. If this minimal sum is greater than D, then all the sums that you are going to take from the other element differences, they are definitely going to be greater than D, right? So we did that as that only. So this is our new interval after removing the after incorporating the equality sign. So I did that, and note that these these are going to be in zero form, zero indexed. So I just check whether low is less than or equal to high. If this is true, I convert it into one based indexing because my Fenwick tree is implementation is one based, right? I converted it into one based, and this, what is this? This is just finding the y's such that they are conflicting with our d of r. or X or the new element we are adding to the good window, right? So we just finding all the y's. So if the sum from this range L to R is greater than 0, which means that at least one element is present in this range which is conflicting with y. So I'm going to remove that occurrence. So that is present at the left pointer, as I said here, that that element, where is it? Uh, uh, yeah, yeah. If the left pointer that we're maintaining, if it is going to conflict, then we're going to shrink the size of our subarray, right? Right. We're going to shrink the size of our subarray. So we just add -1 to the position B of L. And what is ID? ID is a function. Note that B of L and B of R can be up to 1e9, and so the size of the so the size of the fed victory, does not, explodes. We are going to convert it into ID. So basically, ID is going to return you the position of this element in your compressed array, right? So this is just lower bound of the value that you passed, right? This is pretty basic if you know coordinate compression, right? I highly recommend that you learn it from some online resource, right? So if you do that, now your entire subarray range has become good because you have removed all the conflicting pairs of L of R with the current window size. Right? This is done. Then you just add the element R to your Fenwick tree, and then you just take the contribution of all of these. You know, as I said here, if some array from L to R is good, then you can just take all the pairs from L to R, right? So this is R minus L plus 1 and just find the answer, right? So this was fairly simple. The implementation was simple if you know about Fenwick trees and corner compression. None of these was, you know, out of the box thinking. You just need to compress this. Uh, you just need to, do this maths that if you just need to take care of the adjacent pairs only, and you have to solve this equation as well. So if you were able to solve these two equations, then the implementation would have been easier, right? And I submitted that. That is going to work fine, right? All right. So we discussed all the five problems, right? Thank you.